spatial and non-spatial data models. In this lecture, you will learn about data models available to store GIS data. Like you may be knowing, you are having data models named Vector, and I think there is some audio problem. Am I audible?
Yes.
Okay, so in this lecture, you will learn about different data models, vector and raster data models, and some non-spatial data models also. This lecture is delivered by Mr. Asutosh Kumar Jha, who first will have a recorded session, and at the end, you can write your questions in chat box. You will see your queries at the end of the lecture. Even during the lecture, if you are having any question during the session, then you can write the question in the chat box. We'll address at the end. One participant is saying no audio. Is it the person specific problem or for all? Yes, I think if someone is not getting audio, you can reconnect and let's see if problem is resolved. So now we can have our lecture. We can start the lecture now.
These lectures will be trying to understand the basic data models which are in use, especially by different GIS software. I recently developed additional formats like GeoPackage and also the KML formats, and also how those data sets are actually internally organized. So we'll be seeing all those under this uh, lectures. So basically what I have thought is that in these lectures, we'll just try to understand and to find out why we need to have a data structure. So basically why in GIS analysis and how does the GIS analysis dependent upon the different GIS data structures. A few basic GIS data structures like raster and vectors, what exactly it means, what are the basic structures which is almost equally being represented in a different type of file formats. Then we'll also try to understand a bit. Good afternoon, good evening, good morning. So from wherever you are, I'm just wishing you according to that time. And today is basically under these lectures, we'll be trying to understand the basic data models which are in use, especially by different GIS software. Recently developed additional formats like GeoPackage and also the KML formats, and also how those data sets are actually internally organized. So we'll be seeing all those under this lectures. So basically what I have thought is that in these lectures, we'll just try to understand to find out why we need to have a data structure. So basically why in GIS analysis and how does the GIS analysis dependent upon the different GIS data structures. A few basic GIS data structures like raster and vectors, what exactly it means, what are the basic structures which is almost equally being represented in a different type of file formats. Then we'll also try to understand the basic of spatial relationship and the importance of topological representations. So those are basically required for carrying out topological based analysis. Then we'll also see a few examples of the file, how those are actually organized, how does it look like in your computer systems, and how does it look like in a GIS environment. So we'll just try to see all those different file formats. Along with that, a few spatial data formats which may not be a part of GIS data structures, but which may be required and people have used it for different applications. So we'll see a few of them. Along with that, we'll also see the example of the open standard based data models like KML, the GeoPackages, GeoJSON based formats, and so on. So let's begin with a simple problem in GIS. So as you can see in this map, what we need to find out is that how can we reach from a place A to place B. So in this case, place A is actually an Institute of Remote Sensing, and place B is actually a clock tower, so within a city, and it's one of the landmarks which is available in Dehradun. So if you are new to this place, then in those cases you might be interested then how to go from place A to place B. So this small problem may look very trivial if you are using a Google map. If you don't know, you just put from to, and accordingly you will be getting the output. But earlier also, and in the current systems, if you want to build a kind of Google map based applications, then in that case, you need to fulfill this requirement. You need to organize your data sets. So if you see in a GIS data set, whenever we create, or in reality, you'll be having a lot of information available to you. So like in this case, we are seeing that there are satellite images and there are multiple informations like different places, important landmarks, few houses, and so on, which is the part of your reality. But to carry out this analysis to find out the routing problem from place A to place B, you need to organize these information. So what you need to do is you need to filter out few of the information which is available in the reality into your computer systems, or you say any kind of analysis systems, where you need to do a filtering of the information which is available to you, and then on the top of that you are going to run an analysis. So in this case, you may execute few of the path algorithms like shortest path, shortest time, and so on. So there might be a multiple options which may be available to you, or you may be interested in top 2, top 3 shortest path, or what are the other alternative routes, and so on. So those kind of informations you can carry out. So for in this simple examples, we are having a small GIS requirement that if anyone is giving two places, this would be able to find out the shortest path. So that's basically GIS requirements which any human person will give. So like any lay person, if you are interested from going one place to another place, so you'll be putting all those questions. That questions has to be converted into a GIS-based question. So that GIS-based question means you have to have an algorithmic GIS algorithm which is going to take these inputs in such a way that it is going to give you the shortest path output in a GIS file formats, and finally you are going to represent it in the answer form. So in this case, it is being displayed as a map. You may also have a few additional text informations. Sometimes you may also be having a navigation assist. So all those solutions, whatever you got, can be represented into a different human interface format. So generally, to carry out these processes, what we need to do is whatever data sets we have to convert, or whatever the GIS requirements which has been provided to us, we have to first break these requirements into the kind of algorithm or analysis which we need to carry out. So that first part, and another one is that how the data which can fulfill that particular GIS requirements, we have to look into. And these two, that is basically the algorithms and corresponding data, goes into a GIS data processes. Those processes may be very simple software like QGIS, or it may be very complex distributed computing-based systems as well, like Google Earth Engine and so on. So it can be a very different type of processing environment, but all of those processing environment will require some kind of data organization and interactive analysis algorithms. And finally, those processes is going to give you the output which can be represented and provided to the end user. So that's how we get answers. So in all these, the GIS requirements are being raised by the humans, and answers are also being expected in the human language. And the whole process is being carried out in a machine. So we'll just see that how the data is being organized in a different machines. So to coming back to the same problem, how we carry out the human based analysis in general. So let's say if you are new to this place and think of a situations where you are not having any mobile phones available to you, no internet connection. So you will just go and try to find out basically the information that how you can reach from a place called IRS to another place called clock tower. So these two informations are there. So you will ask anyone who is there on the road that I want to go to the clock tower. Can you just tell me how I can reach there? So once he understands that what is your origin and destinations, or what is your destination basically, so what he will do is he will try to give you a few landmark and important roads. So he will say that you go to take a like in this case the Kalidas Road, which is again connects to the New Kent Road. And from Kalidas Road, you take a right turn to the New Kent Road, and finally you will be reaching to the basically Rajpur Road, which you travel straight and you will be reaching to your destination. So you'll say that how much time does it take? So it is going to take 8 to 20 minutes. So that's basically the information which you are going to provide to the human, and he will answer it to you. But for computers, what we have to do is we have to provide a kind of informations in form of numbers. So that's what we call it a coordinate-based system. So we are having a like location A, what's its coordinate, location B, what its coordinate, the corresponding attribute informations, like what A is called in this case is IRS, and what is the place B is called. So these are the basic informations which is available or which is required to solve these problems. In human-based, you just need to have an attribute, and based on the experience, people will tell you that how you can navigate from place 1 to place B. So if you're having a detailed information like the name, place, then corresponding latitude, longitude of start and end points. So what happens is we look for a kind of informations which can be represented in a machine. So in this case, we are having 2 point locations. This is basically a latitude and longitude. So that is nothing but a point geometry, which we call it. Different type of roads are nothing but a kind of straight lines, which will be having few starting and ending point. And in between, you will be also having few intersections points where other segments, the line segments, can also be joined. So that's basically a line segment-based geometry. So roads are generally represented by that. And then if somebody wants to know how much time does it take historically, or what is the expected time, so those are the additional attribute informations. So especially to solve that how you can reach it, you don't need any attribute informations. The start and end point and corresponding connective networks of different segments would be sufficient for you. But if you want to have some additional information like how much time does it require to reach, is there any alternative routes where we can have shortest time and so on. So if you want to do a kind of evaluations, in those cases, probably you will be needing some additional attribute informations. And based on these machine data sets, the shortest path algorithms can run, and it can give you very beautiful maps as we have seen in the previous slide. And it will also tell you detailed information of how much time. We'll be having a lot of need to have the spatial informations. So those spatial informations are being represented in systems where we can put it any place in form of point. And generally those points will be point formats and corresponding locations will be there. Then if you connect those any of the points, you'll be having a line segments. Those are called lines. Again, those lines will be having multiple segments. So those are basically line segments. Then you may also have polygons, which is depicting an area. So these 3 basic geometry are there, which can be used for representing the spatial informations. Along with those spatial informations, you also need to have a few attribute data. So those attribute data are important as we say that what is the place, or what is the name of the place which is located at corresponding latitude and longitude and so on. So if you want to query such kind of questions, if you want to find out an answers to such questions, then in those cases, the point details like name, similarly the line, road length and so on has to be provided. So those are called the additional attribute which is attached to, or which is having attached to all the geometrical informations which represents a particular features. Along with that, we also need to have a few additional auxiliary informations which may be required for other purposes, like what kind of coordinate systems we are using. In case of visualization, we need to have a proper extent, the different type of scale, what is the scale on which the data is acquired and so on. So those are, or maybe in some cases, we may be interested that who is the maintainer of this data set, so that you can ask and get the information about the when this data was created or what was the processes and so on. So those are the additional auxiliary data sets which may be present in your GIS data sets. So in nutshell, if you see that the GIS data set will have or will be consist of an attribute informations, the map data, that is map data is nothing but whatever you see or spatially. So generally in case of 2D formats, you'll be having vector and rasters. The basic pin formats are also there. Apart from that, there are other 3D based GIS data formats are also available to us. And then these attribute and map informations or the spatial informations can also be inserted into a databases, which may be relational based databases like PostGIS, where we add few additional functionality in form of PostGIS, and there you can insert or you can keep all these informations inside a databases. So if you see that the map dataset, whenever we say, generally it should be a kind of vector data, raster data, and corresponding clean data. So we'll just see a few of those example of these. One important aspect of all the GIS data structures is that we need to have some kind of referencing systems. So those are coordinate systems and corresponding location referencing plane. So coordinate systems are generally a representation of space in 2 dimensions. And since our Earth is not flat, so we need to have some kind of projection systems where this 3D information can be put into a 2D system. So those are basically local reference plane-based systems, and we call it as a datum, finally getting converted into projection systems. So location, the specific location-specific reference plane, the coordinate systems is required, which will be as a base or which will act as a auxiliary informations. So once you have these 2 informations available to you, you can create a simple X and Y based systems where we can have a multiple locations, and these locations can be represented in form of tuples. Like you can say what is the X values and what is the Y values. So tuple of those can be used to represent. So each of those points we can represent it as a spatial point. So it can be a latitude and longitude based, or maybe some fall system, fall northing in the projection systems can also be added, and you can have another projected reference systems. So you can have the data set represented in a vector format, and you'll be also having a raster format. Raster format is nothing but the data points are actually, or the space are being filled with a regularly spaced grid, and each grid is going to have values which will depict that the whole area within the unit of this grid is basically the place or the information where the place information about that place will be stored. In case of simple triangulated irregular networks, that is called TIN format. So in TIN format, we not only represent the 2D, but 3 data sets can also be represented, and we can create a translation-based systems. Few algorithms are there which can be represented. So if you see the GIS data structures in all of the basic representation of GIS data set is going to have these essential components. So a special or coordinate system, that is CRS based systems, will be there along with the corresponding detail that which format is there, that has to be there. All the geospatial data sets or the different information in the GIS is there. There is one important aspect which is called topological relationship. So generally, in any kind of GIS or spatial analysis, we need to understand that what are the few basic relationships which may exist between different objects. So if you see that in this case, the total 8 different spatial relationship is being depicted. So like in the first case, we see that it's called a disjoint. So under the disjoint, what happens is that you say that one feature is not connected to the another. So these features can be anything. For example, there may be a water bodies which may be represented by a red color boundary with hash patterns, and you will be having a black boundary features which may be a columns. So you'll say that there is no connectivity between the different settlement areas with the corresponding water bodies. So if you want to say that, then it should satisfy that there should not be any component or any node which should be connected with each other, or there should not be any connection between these two features. So if you are having such two special objects, then you can say that this relationship is actually a disjoint. So these joints may be along different features. So you may say that, let's say you're having one featured data sets where you call it all the water bodies you may be having as in one single informations. And you may also be having, let's say, all the settlements which is available in other layers. So you can have a disjoint relationship between these two separate informations, or you can also have a disjoint information, disjoint relationship within the same data type. So it means like these two features may represent two separate water bodies which are not connected. So this relationship which is being shown in the disjoint can exist within the data set, in a single kind of data sets, or different kind of data set may also be there. So there are other relationships like meet. So in the meet, we can have minimum one particular node point which should be connected between these two features. So if you're having any kind of connectivity established, even in form of a node, not there may be that cases where boundaries may not be there, but these two are connected. So for example, let's say if you're having two different villages and these villages are connected by a bridge, so then in that case that bridge can act as a node point, and which will say that these two villages are connected with the node points. Then there's an equal relationship, so it means like all the nodes which is present in one particular features has to completely cover the second node. Then if you're having then there's another relationship called inside. So second feature has to be completely inside the outer features. So it means like in this case we'll say state is inside a country. So like you may be having multiple province and other structures. So all those administrative boundaries within a country will be inside the boundary and inside the country. So that's the basically the inside relationship will show. The reverse of inside is covered by. So it means like you can have a multiple districts or maybe a province or maybe states which combined together makes a country. So if you want to say that all the smaller areas which are being covered by the larger portion, so that kind of relationship which exists. So it's a kind of inside and covered by is a just change of the operator, and the perspective of the relationship changes. Similarly, we are having contains, covers, and overlap. So as from the basically the representation, it should be clear. So these are the different spatial relationships which exist in any kind of GIS data sets. So what is expected in any data structures for carrying out the GIS analysis, that your such relationships should always be preserved. So if your data structure supports that, then we call it as a topological relationship, which is existing between different features. So what exactly is the topological relationship? So topological relationships are nothing but the kind of properties which are conserved across any kind of translation. So it means like if you're changing a point from one coordinate system to another coordinate systems, you are just wrapping or doing any activity, stretching, or any kind of activity which you do, the spatial relationship which exists between the different part of the objects should not change. So the simple animations is basically showing that the different part of the paper, whatever on the paper, the different parts. So all these different parts, whatever you're having, these parts are always connected to each other, even if you do a transformations of these 2D paper into a 3D format. So if your transformations maintains the relationship, you are not tearing it out your paper and so on, then in those cases the topological relationship is existing. So origami is a kind of method where the topological relationship is being maintained. Then these topological relationship can be used for identifying the directions. So once we have built this topological relationship, then in your GIS dataset, you can create a directional aware processing techniques. So it means like you'll be able to tell the left and right of the road. So what are the features? Or you may be telling that I want to see only the water bodies which is available on the left side of the road and so on. So that direction awareness processing will be possible if you're having any kind of topological relationship. And apart from that, you can also have a few metric relationship like distances and so on within in a topological relationship. So these are another important aspect which any kind of modern GIS data structures should support and is nowadays is trying to support these relationships. So let's see that how the data set, especially in the vector format, is being represented in your different files. So if you see any kind of GIS data set, so it will look like you'll be having a few files, like in case of most widely used is the save files. So we'll be having a directory which will contain a few files like SHP, IDX, ending with .shp or .idx or .crs and so on. So there will be multiple files which will be present in your directory, especially if it is containing a shape files. But in all those, inside those files, the information is being organized in a way which is a kind of, this is basically a cartoon representation of that organizations. So here you're having a kind of point data. So if you're having a point, then you're having basically a line and corresponding polygons and so on. So if you're having such informations, point, line, and polygons, so generally you need to maintain it in some format. And in this case, as we see, that the point is being organized as a tuples in the case of X and Y, and this point is named as a point number 1. So this point number 1 corresponds to the location of this. So you will say 1 point something that can be fractional part can also be represented in case of vector data. So it will not be the whole number, it can be a fractional number as well. So for these points, we'll be having one entry. So whatever the representation of the points will always be kept in a file. So like in this case, there are multiple points. So those points may be an independent one, or those points may be a part of as an in segment, as an in point of different segments, or intermediate point of 9, or it may be those points may be the corners of the different polygons. So whatever points which you are having, generally all these points has to be represented as a pair, the order pair. If few of these points makes a line, so what we do is we create a list of points. Those are called a node list. And if you are also interested in preserving the topological relationship, then you have to say that what is the starting and ending point. How it is important, we'll just see at later stage. So you'll be having a starting and ending point, then corresponding informations can be stored. So if you want to now create a line, so you have to say what is the starting point, what is the ending point, and intermediately if I want to traverse the whole line, so which all nodes I need to travel from location A to location B. So like in a line number 1, which is represented this red color line, is actually consists of 4 points or 4 nodes, that is 1, 1, 3, approximately point number 2, point number 3, and point number 4. So these 3 points basically creates a line. Same way we can have a polygon. So polygon may be consist of multiple lines. So it's basically building the hierarchy where the polygon is consist of lines, lines are consist of points, and that is being represented in a proper reference coordinate systems. Those reference coordinate systems can be a projected one, or it may be a geographical coordinate systems like lat-long. So if you see the basic examples, or if you want to create your own data sets, or you can say the examples which is being represented here is called spaghetti model. So earlier when GIS started, so it is started with a simple spaghetti model where file used to contain only the informations like this. So in this case, what you have a different area, different features. Like in this case, you're having a feature A, feature B, and feature C. Now feature A is nothing but a kind of polygon. So you say this feature A is consist of 6 different points. So this feature A is consist of point 1, 2, 3, 4, 5, and 6. So all these 6 points belongs to that. So you say feature is consist of 6 points, and then you put all the 6 points coordinates below that. So if somebody wants to read the whole shape of the feature A, that is the polygon A, then he will just keep it at the first. He will see there are 6 nodes, so next 6 lines he will be reading. And on the basis of that, he or she will come to know that there are an order pair, and these order pairs are the part of that particular polygon. So this is basically a representation of the polygon. Same way, if you're having only a point, so you'll say point feature B is consist of 1 point, its corresponding location is 4, 4. Or you may also see that you may also say that feature C is consist of 4 features, 4 points, and the corresponding coordinates is being represented below. So if you create such kind of data structure, this is called spaghetti models. So earlier the GIS used to be stored in that format. In fact, nowadays also people are exploring this format, especially for the larger data sets of the big GIS kind of cases, because the big GIS data set cases, the proper indexing and querying is still not integrated. So people use this spaghetti based model there as well. If you want to build a topologies, then as we have seen that which is actually is being used in ArcInfo5, which was the earlier standard file supported by the ISRI, and that was the proprietary file. But nowadays you can even open those proprietary format directly into an open source based platform, because the format representation has also been open. So in that case, you will say that each line is nothing but an arc, and this arc will have start and end point. So you'll be having point 1 and point 2, and it's the first node and second node, and corresponding arc number 1 is being given. So you can create an topological relationship for lines. Similarly, you can also create a topological relationship for an area. So you can have the arc 1. It may say that starting from point D to C, so that's basically the representation of the arc. Along with that, this arc, you are also storing that which feature is on the left and right. So it's basically a 2D shape, which or the 2D area where left and right relationship are also being stored. So if you want to build, or if you want to support any kind of topological relationship, then in those cases, if it is just a point line based, then start and end nodes would be sufficient. But if you're having an features which is also being required to be represented as a node, as an area, then in that case you have to say that the one arc. Along with that, you will also need to say which feature is on the left and right. So if you put these 2 informations, then you will be able to make sure that the topological information is present in your data sets. The spaghetti model was basically a single file, quite cumbersome to read and process. So what people have tried a different kind of representation. So what they did is they splitted the informations about the point into one file and polygon into or the other features which makes any kind of those points are being put into another file. The advantage of these has been that once one point is there, and if you are creating, if that point is a part of another features, then there won't be any second entry as was required in the spaghetti models, and you'll be having a saving of the spaces. However, in such cases, especially the vertex dictionary format cases, you will not have any kind of topological relationship. In fact, in few of the programming uh, libraries which supports directly such kind of vertex dictionary, which you can easily create even in a simple programming library if you are interested to create in your custom program. Otherwise, you may directly deal with all the GIS information in GIS software. Then if you want to build a topological relationship, the same got extended in the file, the corresponding polygons, and then you'll also have a relationship tables as was being given earlier. The same topological relationship with respect to the area and other things is being given. One important thing which we need to see over here, that there is a special kind of polygon which is called external, which is which can be thought of as any area outside my extended or within my study area or within the extent of these boundaries are called a external polygon. So those are the special polygons which is created by the systems. Then later on, the other proprietary format like ARC has come, where the basically the vertex and arc concept was there. So it is just a kind of similar informations what we have seen earlier, but the information was organized into a multiple file in the form of tables, like arc will be, or the line will be arc ID, corresponding start node and all the intermediate vertex points. So those information will be represented. Same way arc topological topologies, the different polygons topologies and so on. So there are multiple files which was created under the arc vector models. Now we just go to the raster grid coordinate system. So this becomes understanding of the underlying structure becomes an important aspect, especially when you deal with multi-source data format and which may be having a very larger swath kind of information. So it means if you're having a larger swath informations, then your pixel is no longer remains as a square, but rather as you move away from the equatorial plane, your pixels will be larger and larger, and as you come into the equatorial plane, the pixel will become smaller. So you'll be seeing that as you move from equator to the polar systems, your grid systems or the size which you might have decided at an earlier at equator maybe start compressing. So if you're having a data format which covers such a large swath like AWIPs and so on, or maybe spot and so on, which is having a very large swath. So in those cases, the curvature also plays an important role. So in such kind of systems, sometimes what may happen is like there may be a specialized data set which you may be getting from the, let's say, weather department or the meteorological departments, which may have collected the information from different stations, and they will give you in a grid format. In a gridded format. So if you want to bring out the synergy between different data sets, so you need to basically understand that how the information which is supposed to be a part of any raster data sets are expected to be represented. So in most common way of representing the raster grid coordinate systems is that it will be a kind of regular 2D grid. So it means like you'll be having an equal size along horizontal and vertical directions. So you'll say 50 meters, so it means you'll be having a 50-meter grid, and the length and breadth of this grid will be 50 meters. And all the informations within this grid or this rectangle or cube size grid, it is expected that all these information will be located at the center of that grid. So this is by default in most of the software assumes that, but in some cases you may be getting, especially in the weather stations data sets which we get interpolated, we may be having the information which may be represented as the coordinate corner of left or right corners. Generally it gets represented. So if you are dealing with two different sources of the data, then this particular differences are expected to be explored at the beginning itself. Otherwise, you'll always have a kind of uniform bias across, and the matching will not be. So in general, the raster grid formats are regularly placed grids with equal size in width and height, and information will be expected to be located at the centers. And these information located at the center may be considered as a part of stored values of any processes. So those any processes, whenever I say, so it means like it can be a remote sensing based output process format. So it means like you're having a sensor, camera on the top, it just collects the radiance informations from the ground and stores it in an aggregate format where you can assume that that radiance is actually located at the center of the grid. And that's basically one of the processing functions. Or in most of the time what happens in the GIS is that we have to deal with, or there may be a multiple layer interacting with each other. For example, let's say if I want to create any kind of suitability analysis. So to carry out the suitability analysis, there might be multiple layers. So one may be distance to few features like schools, colleges, and so on. And then all those multiple layers will interact with each other to give you the output. So in that case, the functions can represent the operations among the different layers of the layers, and that it can represent that. This function can represent that, and that information will be stored. So it's important to understand that the information are expected to be located at a half pixel distance from the corner of each of the in most of the raster grid format. Another important thing which we need to understand is that whenever we create or represent any information in a raster format, then the shape is no longer preserved. So it means like the smooth boundaries, whatever we are expected to see, those smooth boundary will no longer will be existing. So in this case, as you see that the polygon is being represented as 2 and these 5 grids. So that's basically the polygon which is being represented. When I rasterize this line, so this line got now converted into a checkered staircase effect, you can see, and that pixelated format, it will look like this. And point will no longer be a unique point, but point is expected to fill this whole grid and located at the center of this row and column. So that's how the raster data, whenever any kind of geographical object is there or phenomenon is there, that will get represented. So this is just an example of if you are carrying out, let's say you're having a vector data and you are carrying out that analysis in the raster-based operations, then there will be a kind of rasterization effects. For example, in this case, you can see that there are lines are there. So these lines are quite smooth, but when I rasterize it, then it loses that smoothness of geometry, and it corresponding informations and corresponding staggered staircase effect is being shown. Same is also the case with the polygons and so on, which we are seeing it here. One important thing which we need to see or observe over here is that if you are doing a rasterization of any vector file or any vector-based system file format into raster-based file format, then what happens is the information whatever is present in the vector format, after rasterization it may be lost. So just an example of this, that this is basically a river body which you are seeing it over here, but after rasterizations there is a discontinuity over here. So that's basically the effect of rasterization cases. The reason for that is that during the rasterization process, it fills the grid only if and only if the total area within the grid represented by this polygon is more than 50%. That's the default operations or default processes which is being carried, and accordingly there will be a lot of discontinuity. So in case of very thin, smaller polygons, thinner geometries, there may be an impact of that. This discontinuity may arise, and it has its own implications at later stage whenever you will be doing any kind of spatial analysis. So in case of raster data, there are ways of storing the information. So generally, the information are being stored as a all the grids will store some kind of informations. So if your features are not is not falling into any of the areas outside this feature box, it will have some default values. Those are called null values or NA values. So generally, any kind of GIS data will also tell you that what's the default NA value which is being supplied to you, and you should be aware of that. Again, that becomes an important parameters to be considered while doing an homogenization of multiple data sets. So we'll be having in this case, basically each of these grids will store the values, and the values are nothing but in this case it will be an NA and null values, and that will be provided over here. And you're going to have and all the places which the values are stored, like in this case the red color is representing a kind of area. So it will say it will have some attribute values. So in the images, for example, in the images you may be having a radians to DN conversion, and finally you will be having a few DN numbers which will be stored. So that's how the general raster data sets is being storing. But in this case, you see that we are storing all the informations, and there is an increase in file size. So to avoid that, what people have come up is that there's a compression techniques. So like the run length, chain coding, block coding, and quad tree are a kind of different compression technique where information are being stored based on few basic principles. Like in this case, if you move from beginning to the end, you look for in a row the continuity of the values. So in this case, the first row is null value or zero values, and there is a continuity of that value still beginning from the end. So it means from 0 to 8 or 1 to 8, all the columns is going to have a zero values. So we can simply represent 0 is repeated 8 times. Similarly, the second row, if you see that 0 is repeated 4 times, that's what you write, 0 is repeated 4 times. Then 1 is, that is your attribute is repeating 3 times, and again 0 is repeating 1 time. So what happens is for each of those row by row, the continuous, the value and the continuity of that value is till what point, how many times that continuity is existing, that you are storing it, and this is called run length encoding, which is being used for grouping of the data sets. Similarly, we are having a chain coding. So in the chain coding, we only look for an outer boundary and specifically used for storing the polygons features, where outer boundary is being taken continuity as a features. So like in this case, we'll be having a starting point 5, 2, and from there you have to move eastward 3 times, southward 4 times. So if you, from the east you'll come here, then west 1 time, then again south 1 time, west 1 time, and so on. So this basically covers the whole outer boundaries. And if you provide, so this is called a chain encoding, which is being used for representing the information around a polygon fill. We may also have a polygon fill with the blocks. So you can have multiple blocks, and we can say block coding systems, where we can create a largest block of, like in this case, this whole area is having a largest block, and starting of that block is 5,2. Then we are having a block size of 4. So it means these two blocks are there. So there are two block sizes of 4 and their corresponding starting point, which is being represented in this case. Similarly, the left 1 blocks. So if you want to reconstruct this whole data set, you can read the whole block size, and based on that placement of that, you'll be putting those values, and any other places you'll be simply putting the null values to reconstruct back the whole area. Then you're having a quad tree. So basically what it does is it continuously divides the total images into 4 different blocks till it reaches to a point where all the information present in the blocks are of the same nature. Like in this case, these oranges are of the same color, so there only there's no further split is happening at the first block, so it will remain over here, and there is no further block, and this is being stopped. But at later stage, when we see, like in the block number 2, the largest block reaches as the green colors are 3 with block size of block count of 4. So these 4 blocks are there, and then you're having a left block which again gets splitted further, and so on. So this is basically a quad tree encoding. And just on the same principle, the quad tree indexes are being created, which are being used for different spatial analysis of it. So if you see in a vector and raster data formats, basically there are a few basic differences are there. So vectors are also called object-based models because you can create very smooth boundaries, which you can create in a vector-based format, but in the raster-based that is not possible. And the whole one cell will be filled, and corresponding staircase effect will always be there. In a vector-based format, the points, each and individual points has to have its locations stored. So it means each of the node, it may be an independent node as a point, or it may be a part of a line, or it may be a part of polygon. Individual nodes and corresponding locations has to be stored in a vector format. So, and that is also in correspondence to the whatever the coordinate reference systems you are having. But in case of raster, what happens is the different locations can be accessed in terms of simply X and Y or row and column locations, and that always will be with relative to the origin or the original point lat long value. So corresponding lat long of origin lat long values will be storing, and then based on the what is the row and column number, corresponding row and column size can be added, and on the basis of that we can get the raster values. Then vector format generally take less spaces because you are storing only a few information of the points which gets created. In the raster base, you need to store all the informations about each of the grids within the extent. So generally it takes it, the sizes of the raster files will be quite huge. Then in the vector, the units are, or the basic objects are the point, line, polygons, where in case of raster, the basic objects are cell. In a vector-based analysis, we carry out the geometrical analysis, and that's the geometrical overlay analysis, which requires a kind of geometrical computations like, there are few algorithms to find out that if the point is intersecting, if the 2 polygons are intersecting, or is a point is a part or inside within a polygon. So all those are basically a geometrical based analysis which can be carried out in a vector. But in the raster cases, the raster layer data sets are already, and the grids are predetermined, so you only have to play with the corresponding grid values. That's why it's a simple algebra-based operation should be sufficient for carrying out the raster analysis. In the vector, all points are referenced, where in case of raster data sets, only the basic origin point has to be referenced. And then based on the cell size, you can just compute the different cell locations that can be represented. And the few formats are like SHP, GOT format, and so on. Along with these vector-based formats, there are 3D formats like which is being used to store the information is called a TIN model. So TIN model is nothing but triangulated irregular networks. So which stores the information in an X and Y coordinate and Z coordinate, and corresponding it creates a different triangles. There are a few algorithms on the basis of which these triangles are created. And these triangles, locations, and corresponding adjacency is being stored in a TIN model. So it's a simplified model which can be created from benchmark points, your own user input points, and so on, and can easily be created in TIN models. So this is a representation of the TIN models and how it's being stored. Apart from that, there are a few specific formats which may require for specific applications. For example, in a snapshot format where you need to have a unique grid, but those grids are actually being stored as at a different time interval. So you can consider it to be a kind of cube where X is the locations and in the Z direction you'll be having a time. So with that, the information snapshot is being stored. So like nowadays you're having a special cube kind of concepts which is being applicable in Google Earth Engine and so on, which allows you to do a temporal analysis that can be carried out. So there the data is being stored with a fixed grid and corresponding time, and for each of the individual time period, the information is being stored. So that's basically, and this is also called snapshot models, where each time you take an image and you carry out the storing the informations. Then there are space-time composite informations. So this is basically a kind of creating a maximum composite of all these layers. So where you will say where the changes has occurred, where no changes has been there. So accordingly the information will be stored, and then you can decode that information to come out that you can come out with the information. So snapshot and space-time composite, as you can see, that there's an improvement because if you are not storing all the layers, a single layer itself can be used to get or decode the information which is present in a snapshot-based model. And then apart from these grid-based models, you're having an ST objects models where starting from the basics shapes, then each of the individual time in a tree format is being stored, and the corresponding whatever it is getting decomposed into multiple components, and further it is getting created. So once you want to create a composite view, so you can think of that each slices represents a spatial plane, and in the temporal dimension it is showing that for how long this particular status existed. So you can use it for finding out the interpolations which may be dependent upon the time and so on. So on the basis of that, ST objects models can be there. Apart from that, time can also be discrete and things can also be added. There's a specific process-based models, like for a specific processes, you create a triggered-based component, and the event-based model, that is basically an ESTDM model, is just an example of that. And the process-based models can be created, where as the data comes, the corresponding processes may be represented. So this is basically very specific to an applications the information is being. Any question? Okay, so what I'll do is that I'll just quickly go through the how does these there are different file formats and how it's being stored. So like you're having an multiple way of storing these information, especially in the databases. So generally you'll be having a file-based system which we evolved into network and hierarchical database management systems. Finally, in object-oriented and relation-based data model also get created. Nowadays, you're having a big data file formats, which is basically nothing but a plain file format, but indexed and created in a multiple segments. In a relational database, generally the geometry is being stored, and each of those geometries are getting connected to an attribute table. So that's how the connection is being established. In this case, you see that there's a geometry called polygons for different features, and there are and these geometry has having a key like 1, 2, 3, 4, that is the word numbers, and correspondingly it is connected to a word number. And each of those word details like name, its populations, and so on is being provided in this case. This is the file format. If you look for the proprietary file format like geodatabases, so where what happens is that you can store multiple type of data sets in a single place. So it's a kind of directory-based structures where informations can be stored in a single directory structures. So as you can see, like in this case, the personal geodatabase, which can have a feature data sets. So feature data sets will share the same projection systems and all the details. And within the feature data set, you can have a point, polygon, line can be stored. You can also store in the feature data sets with the same projection system, the raster data set as well, so that you can store it. You can also store the network models. Network models are being used for doing a network-based analysis that is being created, and you can store it in a geospatial data sets as well. And you can also have ARC info coverage. So this is basically an example of the different ticks, node, and ARC, which is being stored in ARC info coverages, which you can store it. Then you'll be having a shape files that can also be stored, where the shape file will be in form of TIFF. SHP is the format. It has also an additional file like which will be act as an attribute tables. Along with that, few other 6 like IDX, indexes, files, and so on will also be there. So this is basically a logical organizations. In your file, if you see in the folder, you will see that it will look like something of this sort, which will have multiple files stored and the corresponding information. So if you copy any kind of files, if somebody says that give me a shape file of words, we need to make sure that all the 6 files which comes along with should be given. Most of the time at the beginners, what they do is they just copy the word.shp file and forgets to copy the other informations. And if you don't provide other information, the attribute and other information will get lost. So you need to make sure that each and every individual component of those file which is present in on your hard drive should be represented. So this is just an example of how within the same geodatabases you can store feature data sets, different validation rules, raster. You can also store TIM, and specific local informations can also be stored. Nowadays you're having a few OGC-based feature models. So we simplified the representation in form of tree structures. So we're having a geometry. Geometry can be a point, curve, surface, and geometrical collections. Curve is generally a line strings with line strings, or surfaces can be curved surfaces can also be there. And there may be a geometrical collection which can contain a multiple curve, multi-point, and other informations can be stored. So this is basically an OGC standard, very simplistic view. It's a very vast document which is available on the net. But this is just an example of how simplistic view, especially the spatial view, is being represented. So on the basis of that, it has a few basic geometry like point, line string, linear string, polygons, multi-point polygons, and so on. And it also maintains the spatial relationship between different objects. So that's basically the basic geometry class which has to be there. So few of the example of OGC based data set is like single points, or it can be a collection of multi-polygons. So like you may be having departments which may be consist of multiple polygons. This is not possible in a single shapefile format. You have to have you need to combine all of them as a multiple objects. In OGC format, you can create it as a multi-feature group of collections where each of those buildings will form as a single unit and they will be sharing the same attributes. In case of OGC compliant data formats, geometrical collections can also have point, line, and polygons as a single part. So like in this case, you may be having a department areas where few road connectivity and so on, and the corresponding few important points. So this whole area, you can call it as a point. These kind of representation is not possible in Shapefile, but in case of OGC compliant data formats, such collections can also be represented. So the few of those represent the OGC compliant format is GeoJSON format, so which is nothing but it starts with which is nothing but a text-based formats, and it is having a few attributes, and there are a few annotations are available, and each of those attributes corresponds to the kind of geometry or the collections, is it collections or not, that you can just represent it in a simple starting and ending curly braces. And you may be having a multiple geometrical options which is being defined in OGC like point, multi-point, multi-polygon, and so on. Recently, there has been a GeoPackage format which was basically an effort to bringing out all the GIS related file into a single package. So it means like people should not make a mistake of like in the shapefile, you have to send 6 different files. So what people have said is that that is not an appropriate format because then most of the time the information get missed. So there is a single file format. So GeoPackage is one such single file format, which is based on the SQL light SQL databases and which stores the geometrical attribute and other information in a single file, and that can be given sent across as a single unit of the file. There's a standard basic KML file format, which is again an XML-based file formats. So you don't need any specific tools. If you are if you know what are the structures of that KML format, you can use any kind of editor to even basically edit such files. So with this, I'm just ending the today's session on the different GIS data formats. So if you have any questions, then I'll just
So now you can ask the questions. Basically, you can post the questions in comment box if you have any question. There is one question, can we interconnect one question is, can we interconnect raster and vector form of data for better interoperability? Actually, raster data and vector data, they are different kind of data models. So connection means you can have two layers here, but two data sets cannot be merged. Two different formats of data sets cannot be merged. Either you convert raster to vector or vector to raster. Anyway, they are georeference data sets, so they are interoperable. One data set will be below another one. Another question is India using Oracle database to store spatial data? Oracle databases are, I don't know if anyone is using, but open source community uses Shapefile or Geo packages. And if you go for proprietary ArcGIS, the file geodatabase is used, which is geodatabase system of ArcGIS, and Microsoft Access database, that is Microsoft Access based personal geodatabase is also used. GCS, what is GCS and projected coordinate system? Someone is asking GCS and PCS. GCS stands for geographic coordinate system. PCS stands for projected coordinate system. So in GCS, we have coordinates in degrees. Basically, in GCS, entire globe is represented as 3D. While in projected coordinate system, Earth is projected on a 2D surface. So that is projected coordinate system. So anyway, you will get more clarity about GCS and projected coordinate system after a lecture on map projection concepts and use in RSGIS. So these topologies, yes, will someone is asking, can you tell us how topologies are used for practical? During practical demonstration, we will explain how this topological information is used. Few examples I can tell. For example, spatial queries. So there can be two kind of queries: non-spatial queries and spatial queries. Non-spatial queries are the queries where you can do query on the tabular data, just like in Excel you perform query like select all the area which are having population more than 10, more than 1 million, 0.1 million. So that kind of queries are non-spatial queries. But when it comes to spatial queries, suppose you are having road database and school database, and now if you want to select the schools which are within a distance of 1 kilometer from the road. So in this case, spatial relationship will be used. To spatial relationship intersection. will be used to select the schools which are within 1 kilometer range. Another question is, can we use pin for all objects? Pin is used for representing a surface, not object. Yes, there is another question. How can we majorly differentiate covering and contain? It is related to selection. What? There is another question. Can you please explain arc again? What arc? Hello? So if there are no more questions, we can stop the meeting for today. Okay, then thank you.